starting chapter 4. And pretty much we know how to differentiate everything that we're going to be expected to differentiate. Now we're finding uses for it. So you could think of chapter 4 as being various ways in which finding derivatives can be helpful. And this particular one, this particular use of derivatives is to help you find what's called the maximum and minimum value of a function. And there is, in fact, different kinds of maximum and min. There's one called absolute maximum and minimum of a function, and there are others that are called local maximum and minimum of a function. So imagine this is our guy. So let me show you what an absolute maximum would be. Can you imagine a function that goes up and it goes down? That guy there is an absolute maximum. That is a point on the graph that is higher than anything else. So can you imagine the function had a starting value and a finishing value? And that guy there was say 2. So you would say that there was an absolute maximum at x equals 2. Now, an absolute minimum might look something like this. That guy there is an absolute minimum. And in this case, let's say that's at 3. So we'd say x equals 3. And if they had said, what is the absolute minimum value, you would say it was equal to 2. And if they went and said to you what was the absolute maximum value, you would say it was, in this case, 12. So if they ask you for the absolute maximum or minimum value, they essentially want to know the y coordinate of this guy, right? If they just say what, where, I guess, or tell me the absolute max, or tell me the absolute min, but they don't use the word value, they're essentially asking for the x coordinate of where it happens. Now, as far as that goes, that looks reasonably straightforward. Do you agree? Highest bit in a function, absolute max, lowest piece, absolute min. It does get a little bit kind of grey when you look at functions that have absolute max and mins that are not the top of a hill or the bottom of a valley, which is very common for where they are, right? But an absolute max can be in other places. So since the first 3 questions in your homework are really graphs, let's just use the graphs they've got. Yeah. So here is a function that starts at A, it finishes at S, and we're only being asked to find the value. In other words, we're not the value, sorry, just its location. So in this function here, you might think that C is the absolute maximum, but it is not. Which of these guys, A, B, C, D, R, or S, where is the absolute maximum value of that function?
S.
Is it S? Now, if you look at this function again, where is the absolute minimum? And there's only, in this case, there's only one. Where is it?
R.
I think you said R. Did you say R? Yes. So the definition of what is an absolute max and an absolute min gets a little bit lawyer-esque. It doesn't need to be the top of a hill or the bottom of a valley, right? Although it can be, right? For instance, isn't this absolute minimum at the bottom of a valley shape, right? All you need to do to be an absolute maximum is to be the highest point on that graph. Would you agree at x equals s, the function is higher there than anywhere else? Agreed? That's what makes you an absolute max. Just being taller than anybody else, right? Bigger y value. And an absolute min is being the lowest you could be. Now we have two other guys. These are called local max and local min. Now, you see this hill here at C? It is a hill, but would you agree it's not the highest point on the graph? That's called a local maximum, right? A small part of the graph which is higher than, the rest of the graph near it, right? So can you imagine, no, can't really do that, but can you imagine near to this graph, isn't that the highest part? Now, you see this funny guy down here, which is a little bit higher up than him at B, that's also a local minimum. You see absolute minimum R, local minimum B. Absolute maximum S, local maximum C. And you begin to see the difference between an absolute max and a local max, and same for the right? They can both have the same shape, right? They can both be hills and valleys, but to be an absolute max, don't you have to be higher than anyone else? And to be an absolute minimum, you have to be lower than anyone else. Now, if that was, there's the answers. If that was the case, then it would be relatively straightforward. But here's another complication. And this is a piecewise function. And piecewise functions make the hardest questions to answer. So I'm doing it in no particular order. Do you see at that top of that mountain peak at R? Would you agree that is higher than anyone else? So R is an absolute maximum. Is there any point in this graph that is lower than everybody else? Because that's the absolute min. I think you said A, would you agree?
Yeah.
Yeah, I'd agree. And do you see that little dot? I call them dots and circles, right? Dots solid, circles empty in the middle, right? So that's an absolute min. That's an absolute max. Okay, what is happening at D? What would you call D? Absolute min, local min. I mean, that's really your choices.
Local min.
Yes, and my site's not great. Would you agree that that's not quite as low as here? Right. That's why it's a local minimum. Now, what you might not agree, but this is the definition, so we're going to stick to it, is that at x equals b, do you see that dot there? See that dot at x equals b? It's a piecewise function, so jump discontinuity. See the solid dot where my mouse is? That makes that a local maximum. At that point there, isn't that the highest part of the curve, right? Just a little window of it, and that's it. So you're going to have absolute max and min and local max and min. Now, they don't have it in this picture, but let's move over to C. Now, do you see that guy at C with the little circle in it, the little dot? See that guy? That little circle, I should say. That doesn't count as a local max. Well, you said that did. So why is that not considered a local max? This is where we get the nuances now. What's the difference between that, which is a local maximum, and this, which is not considered a local maximum?
Yes, it's a circle.
Yeah. So you have to have, the function has to exist at the point on that thing. So on this left branch, there's a little circle. So if you see a little circle like that, you can't use it as an absolute max or a local max or a min or anything, right? You can't use it essentially. Okay, this is the third and final one of these. Tell me the x coordinate of the absolute max in this function.
Four.
Agreed. What is the value? That's a different question now. What's the value of the absolute max?
5.
Right. So you see the difference in the phrasing, right? Where it is, it's at x equals 4. What's its value? Its value is 5. Okay. What is happening at x equals 5? What name would you give to that guy?
A local minimum.
Right. And you'd say there's a local minimum at x equals 5. And wouldn't the local minimum's value be 3? Right. What is happening at x equals 2? What would you call that guy?
Absolute minimum.
Well, if it was an absolute minimum, isn't there a piece of the curve over here that's lower? So that stops it being an absolute minimum. Agreed? Right, so if you're not an absolute minimum, what are you then?
A local minimum.
You're a local, right? You can only be one or the other. Well, technically you can be both.
The not filled in circles, like on the right, be considered the absolute minimum, even though they're not filled in?
Ah, very good question. You see the one she's talking about is probably at x equals 7. See that little circle there? Because it's not filled in, this particular curve has no absolute minimum. The place where it would be is where my mouse is, right? Right at x equals 7. But because you can't use circles, right? If a thing's got a circle on it, it can't be used for any of the absolute max and min stuff, right? Or local max and min. It means that this function doesn't have a absolute minimum. Now, a lot of people would say, yes, it does. The answer is 1, right? It happens at 7, the answer is 1. And what you're doing there is you're saying that this function, the lowest value it is 1. Right? But the answer is no, that's not true. Because doesn't this function never get to be 1? Isn't there a hole there? It can get to, I don't know, 1.000, 2 million zeros and a 1, right? It can get that close, but it can't be the thing. So if you see a little circle in a place where an absolute or local max and min is, you can't use it, you don't count it. Are we good so far? Right, so there is a difference between an absolute and a local max and min, right? Can you be both at the same time? Can you be an absolute max and an absolute min? No, I'll say it again. Can you be an absolute max and a local max at the same time? And the answer is yes. Quite right. So, just because it's a local max doesn't mean, just because it's an absolute max doesn't mean it can't be a local max. And let's leave that for the time being. And that is basically the graphing stuff done. So we are getting, or what we're essentially going to do now is go hunting for where those guys are. And I'm trying to find one of my windows, so if you bear with me. Okay, gotcha. We're going to find a thing called a critical number of a function. And I don't think I'm on my right screen yet, am I? Go away, Windows. I'm getting inundated with the wrong windows. Yeah. So a critical number of a function y equals f of x, or the x coordinates of any point on the curve y equals f of x that has the property f of x equals 0 and f dashed x. Sorry, f dashed x equals 0 and f dashed x equals undefined. So the critical numbers for any function are the places, right, the x coordinate, where the derivative is 0 or the derivative is undefined. Because what we've discovered is that these local max and mins, these absolute max and mins, they all live here, or almost all of them live here. The absolute max and min can actually also live at the endpoints. So what we're going to be doing here is getting a function and finding where this happens. And they're very often going to be more than one place. That means we might end up doing a product rule, a quotient rule, a power rule, chain rule. That's probably it, right? So most of the techniques that you've used before are going to come into place. So here is our first example of that, which is question 4. And we have a function, h of p equals p take away 4 over p squared add 6. Now, if you're wondering why these properties tend to give you local max and mins are, would you agree that when the derivative is 0, you're typically at the top of a hill? Wouldn't that be a place where a local max and min lives? Does that make sense? Now, sometimes you get these funny little corner guys, don't you? At those places, isn't the derivative undefined? You know, on one side it's 2 and the other side is -2. But isn't that also the places where local max and mins exist? I hope you're looking at this guy and saying to yourself, I know what method I'm going to use to differentiate that. So I'm just going to ask you anyway, what method would you use to differentiate this function?
Quotient rule.
Great. I think quotient rules are probably the easiest to identify because they're kind of obvious, aren't they, fractions? Now, even to see a fraction, you should be thinking of that guy there's a 6, by the way. I don't know why you can't draw 6 as well. So f dash j, take away f of j dashed over g squared. So we're going to have to figure out what this derivative is. We're going to have to do style points on it. And then we're going to have to go looking for when is it 0 and then when is it undefined. So there's a fair amount of work involved in this. So you differentiate the top, you get 1. Leave the bottom alone, p squared plus 6. There we go, it looks more like a 6 now. Take away, leave the top one alone and differentiate the bottom to get 2p. And then everything on the bottom gets squared. And because I've been, I don't know, pushing it, forcing it upon you, style points is actually going to help us here. So if you're good at making it look pretty, it's going to help us find these guys. First thing I'm going to do is just basically distribute this. So I'm doing style points. That's essentially what I'm doing. Oh God, this is ugly. 6, take away 8p, take away 2p squared. Take away 1p squared, because that and that partially cancel. All over p squared plus 6 squared. I'm just going to write this guy up here again. So you don't need to do this because it's the same guy. I'm going to show you a little algebra trick. If you see a quadratic, there's a very good chance it's going to factor. The problem is this quadratic isn't really written the way we want quadratics to be written. Don't we want them to be p squared plus or minus so many p plus or minus a number, right? It's kind of back to front. So here's a little trick you can do. You can pull out -1 as a common factor. What that essentially does is change the sign of everybody. Would you agree that this is much easier to factor? Right. If you try to factor this, you might be able to do it in one go, but isn't there a fighting chance you'll get a plus where a minus should go, right? You'll get one of your signs wrong. So this fella factors. So we're looking for, is this a factor?
I think the sign on the 8p is wrong.
Oh, thank you. Did it come from? Yes, there it is there. It's not going to change. I'm just wondering if this factors. No, it doesn't matter. It doesn't factor anyway. All that hard work for nothing. So, don't like it when it doesn't factor, but I have to live with it. So that's as good as that's going to get. I was expecting it because you expect WebAssign to make pretty functions, that if I pulled out the -1, I'd get a quadratic and the quadratic would have factored. But evidently, it's not my day for factoring. It's weird. Question 4 and 5 are the same, at least in mine. Ah, well, brilliant. I should have picked question 6. Question 6, you get a guy like that, but he does factor. So I'll do that one next. Well, we're stuck with this guy. Once you've got the function as good as you can make it with style points, what you need to do now is solve 2 different situations. We need to find the values of p that make the derivative as 0. And we need to find the value of p that makes the function undefined. And there may or may not be solutions to one or both of these situations. I'm going to do, I'll do this one first. We are trying to find when this fraction is undefined. Fractions are only going to be undefined when the bottom is 0, right? The top can be anything you like, but if the bottom is 0, it's going to be undefined. So let's see if that can happen. All we need to do then is solve. When is this guy, if it's going to happen at all, equal to 0? Now, I can look at that and tell you that there is no solution. It's not going to happen. Anybody want to explain why I can look at that and say it's just not going to happen? There's no value of P in the universe that's going to make this left-hand side equal to number 0. How can I say that with such certainty?
Because even if you choose a negative number for P, it's going to be squared and make it positive.
Right. So no matter what number I pick here, isn't this going to be positive? Right. Any negative number, square it is positive. Right. And if this number is positive and then you square it, would you agree the answer can't be 0? Right. It's not happening. Is that a good enough argument? I mean, if you want to take it algebraically, if you took the square root of both sides, wouldn't that have to be true? If you try and subtract 6 from both sides, is there going to be a point in this where you say, okay, it ain't going to happen? Can we stop at this point? You're never going to get a P that's squared that gives you -6, and no complex numbers don't count, because in Calc 1, complex numbers don't exist, right? We'll pretend you've never seen them. They don't exist. Right, well, that's great. Back to this one. This darn thing is going to be 0, right? This fraction is going to be 0. Only happens when the top is 0. Does that make sense that a fraction is going to be 0 when the top part is 0, right? 0 over 7 is still 0, right? 0 over 50 is still 0. All you need to do is solve the top. Now, if that thing had factored, which is going to happen in my next question, couldn't we just factor it and get the 2 answers? Right. Since this doesn't, we have to fall back on 2 possible methods. Anybody want to suggest either one of the 2 methods that I could use to solve this guy? How do you solve a quadratic that doesn't factor?
The quadratic formula?
Yes. Does anybody here like the quadratic formula? Because I definitely don't. Right? There is a lovely piece of software called Desmos. That you can sometimes use to get this answer. Now, the reason why I'm saying sometimes is that we want the exact value here. So we can't say 1.414, right? We got to say square root of 2, right? So it may or may not be able to handle that. So let's take a wee look and see what it is. And if it makes it, then we are good. And if it doesn't, then we'll have to resort to that horrible quadratic formula. So I'm typing in y equals 6 plus 8p, take away p squared. And if I shrink this guy and move it around a bit, would you agree that there's a solution here and there's a solution here? You see them? So the answer would be -0.69 and 8.69. And that would be good if they had asked me to give the answer to 2 decimal places. I'd be fine. But you agree there's no square roots in this, so that's not an exact value. So we tried, which means that sometimes, things don't work out right. So we're going to solve 6 plus HP, take away p squared equals 0 with the quadratic formula. First thing you do with quadratic formula is you identify who A, B, and C is. Well, it's been a while since you've probably done one of these, but hopefully you can still remember. Which number, 6, 8, or -1 is considered the A value?
-1.
And the B value?
8.
And lastly, this C value is 6. Now the quadratic formula, which is why nobody really likes it. You remember it? It's just ugly, isn't it? It's not very elegant, but that's the formula. So I'm calling that guy X, but I guess in this case you're going to call it P because that's a variable. So it's going to be the negative of this guy, so that's -8, plus or minus the square root of that guy squared, take away 4 times that guy times that guy, all over 2 times that guy. So it's -8 plus or minus the square root of somebody all over -2. Calculator for this fella. So if I do 8 squared, take away 4 times -1 times 6, I get the answer 88. So far, so good. I do not like the quadratic formula, but we're going to live with it. Now we need to make this answer as nice as possible. Is there a simplified version? Of the square root of 88? Is there anything you can do with 88? Okay, let's phrase it a different way. There is something you can do with 88. Will you tell me what the two numbers should be then?
You can put 2
You're right.
Yeah.
So that's the in-between stage, but you're right. And that gets you 2 square root of 22. Now in this case here, I'm going to split it into 2 pieces. And lastly, divide everybody by -2, that gets you 4 plus square root of 22. Divide everybody here, and you get 4. Take away the square root of 22. And we have finally found the 2 critical numbers. That was a lot of work, wasn't it? So I'm going to do another one, which I already know comes out a little bit nicer, and it's got style points in it. So this is find the critical numbers for the function p of x, and it's x squared plus 2 on the top, and it's a 2x take away 1 on the bottom. So what do we have here? Well, its derivative is going to be another quotient. Now this time things are going to come out much cleaner. Differentiate the top, you get 2x, leave the bottom alone. Subtract, leave the top alone, and differentiate g to get 2. And you get 2x take away 1 squared on the bottom. If you distribute that, you get 4x squared take away 2x. You could probably put the 2 there and multiply through by -2, so you get -2x squared. Almost made the mistake there, -4 over 2x minus 1 squared, which is 2x squared, take away 2x, take away a 4, all over 2x minus 1 squared. And this time, style points do work. Right? Is there anything you could do on the top to make it a little bit nicer looking?
Factor out 2.
Would you agree that we now have a quadratic that does factor? So if you factor x squared, take away x, take away 2, you're looking for two numbers that multiply together and give you -2. So that makes one of them plus and the other negative, right? And the two numbers that you get, right, that make -2, when you add them, you get -1. So what would the combination that would do those two things?
-2 plus 1.
Yeah. So style points has done its job. Not only do we have a derivative, don't we have a derivative that's nice and factored and looks pretty? So we can find critical numbers. The first critical number is when the derivative is 0. So we are trying to solve when this fraction is equal to 0. But fractions are only going to be equal to 0 when the numerator, the top, is 0, which means we have two critical numbers. There wasn't that much quicker than the quadratic formula. Now the other critical number is going to be when the derivative is undefined. Well, this is the derivative. And we are trying to find when it's undefined. Fractions are undefined when the bottom and only the bottom is 0. So we're trying to solve when is the bottom 0. I think that's pretty easy to do. You should be able to do it in your head. What value of x makes this 0?
1/2.
1/2. And the question was, find all the critical numbers. That'll be good. Okay. Why am I not going to use that one after finding it? And it's nothing to do with calculus. It's to do with up here. And it's to do with the domain of a function. If you have a rational function, isn't the domain the usable values of x? can you use x equals -1/2 in this function? So the domain is everybody, right? But not -1/2. So we have to ignore it, which means when you write down your answers, you're only going to write those two down. I think it should go higher. Maybe that's the problem. Yeah. There we go. Little nuances, isn't there? You go and find guys, and then you find out some of the guys can't be used because they're not in the domain. If they had given you this function and said that the values were from 0 to 2, wouldn't I have kicked that one out as well for the same reason it's not in the domain? So watch out for domains. Another one. Yes, we do. Okay. One last one for today, question 7. We have this ugly fraction. Okay, let's be in the hunt for places we can't use. What two values of t are not in the domain of this fraction? In other words, what two values of t you are not allowed to use? Think 141. There's a problem.
4 in the numerator.
There you go. So when we go hunting for critical numbers, if we find that a possible one is 4 or -4, won't we throw those two out because we can't use them? Everybody today has been a rational function. That doesn't mean tomorrow any of them are going to be rational. But at least we're getting practice at the quotient. So you differentiate the top, you get 2t times this guy minus top guy times that guy. If I distribute the top, I get 2t cubed, take away 32t minus 2t cubed minus 32t. They cancel out and these two combine, so I have -64t over t squared, take away a 16 squared. Okay, don't have any style points, right? That's as good as that's going to get. Let's find out when the derivative is 0. Would you agree that this fraction is only going to be 0 when the top is 0? And would you agree that the value of t that makes that happen is 0? So there's a critical number at t equals 0, right? Top is 0. When this is 0, t has to be 0. Let's look at when it is undefined. If this fraction is undefined, that's only going to happen when the bottom is 0. And would you agree that that's plus or minus 4? Would you agree that's 0? Is there a problem with plus or minus 4? And so?
It's not within the domain.
And so we ignore them. which means that in this question, isn't there only one usable critical number, and that's at t equals 0. Right, that was a bit cutting corners, but most of what I did there is valid, right? It's the same thing you would do. I just maybe speeded this up a little bit, but that makes sense, right? Once you've done enough, can't you cut out some lines just to make your thing a little bit more efficient? Okay, last name, bye-bye. And I'll hang about for questions. And Vanessa, just to remind you, if you could hang about, that would be great.
Thank you.
You're welcome. Bye-bye, guys. Last name and bye-bye at least. And remember to keep using your new one. Harmon, have you got a question for me?
Yes.
Okay, you're a little bit quiet. Maybe it's my thing. Let me see if it's my side.
It's probably me. Let me fix that.
Okay, that's better. What's your question?
I may have missed something because I got here a bit late, but what's the thing about our like lower numbers being in the domain, like with a t plus or minus 4 being in domain?
Right. So if you have a function, typically a rational function. So I'm just making one up here. See that one there.
Yeah.
The domain of this function from 141, right? What we call the domain of a function. In English, a domain is usable values of x. In this case, you can use any value of x you like, except values of x that make the bottom of a fraction 0. And the reason you can't use those is because 10 over 0 or minus 4 over 0 is bad news for calculation purposes, right? You can't use it because you can't get a number, right? And a number is the answer. So in this case, we don't want that to be 0, right? And so that makes x equals -3, and that makes x equals 3. Values of x you cannot use. So you would say that the domain is all values of x except for those two.
Oh, okay, so when we're doing the like when is the derivative function undefined, we're looking for the values we can't have in domain.
Well, in this case, they end up being the same, right? But that's only because in rational functions, that's going to be the case, that the bottom is it. But in the way we're not, we're looking for when is the derivative undefined, and it ends up being at these 2 points. And then we say, but you can't use them. So it's a bit like saying, oh yeah, you can have a cake. And then when you stick your hand out, they say, nah, it's too much sugar, you're not getting it, right? So they're tempting you with a possibility, and then we're dragging it back. But not all functions are going to be rational functions. As you'll see tomorrow, there are other functions out there where you cannot, you can have an undefined value that is usable, right? Square root of x has a critical number at x equals 0, right? You can use it, but its derivative is undefined. But in the ones you've been doing today, these are not allowed as critical numbers. Even if you find out that they're candidates, if they're not in the domain, you can't use them. That's kind of what I was saying.
All right.
Okay.